Today we have Dr. Jozsef Pitrik. I hope I pronounced your name correctly.
Yes.
Yeah, actually, I think we are friends somehow on ResearchGate, so we follow papers of each other, and yeah, our research topics, are very close. And today he will present a talk on a divergence center interpretation of general Kubo Ando means. So I hope you like this talk. It's very interesting.
I hope so.
Yeah.
So thank you for the invitation. It is a great honor for me to speak in this seminar. So the title of my talk, as you mentioned, the divergence center interpretation of general Kubo Ando means, and it is based on the joint work with Dániel Virosztek from IST Austria. Now, here you can see the content of my talk. Before diving into the subject matter, it is worth discussing in basics of operator means, especially Kubo Ando means, and barycenters. So at first I will talk about these things. After this introduction, I will talk about three important and well-known examples, namely how can we interpret the most important and best-known operator means, namely the arithmetic, the geometric, and harmonic mean as barycenters or divergence centers. And the motivation of our work is based on these well-known examples. And I will finish my talk with the description of some results of our paper in this topic. Some words about my notations. Throughout this talk, I will use the standard notations. H stands for a separable Hilbert space, which is considered finite dimensional in the most part of my lecture. B of H denotes the linear operators, B of H SA the self-adjoint operators, and B of H plus and plus plus the positive semi-definite and the positive definite operators respectively. When we have got a finite dimensional Hilbert space, for example, the dimension of the Hilbert space is n, B of H is nothing else but the n by n matrices. This is by the n by n self-adjoint matrices, positive semi-definite and positive definite matrices as well. And B of H can be achieved with the Hilbert-Schmidt inner product, which induce a norm in a natural way. This is the Hilbert-Schmidt or Shetland 2 norm. By these, B of H become a Euclidean space. And D squared denote the first and second Freshet derivative respectively. And in all my talk, we consider the Loevner order, induce the positivity on the bounded self-adjoint operators. That is A less or equal than B means that B minus A is a positive semi-definite matrix or operator. The axiomatic theory of matrix or operator means was developed by Kubo and Ando in their fundamental paper in 1980, which served to generalize the notion of means of positive real numbers to positive matrices. In their definition, a binary operation sigma on positive bounded operators called operator connection satisfies the following conditions. The first one is the so-called joint monotonicity. The second one is the transformer inequality. And this is the upper semi-continuity, where this arrow means that AN tends to A from above in the strong operator topology. Especially an operator connection sigma is called an operator mean in Kubo Ando sense, or Kubo Ando mean, if satisfied besides that identity sigma identity is equal identity. Sorry. And an operator mean is called symmetric if it's symmetric. So A sigma B is equal B sigma A for all positive A and B. The fundamental theorem of Kubo and Ando says that there is a one-to-one correspondence between operator connections and operator monotone functions on positive half-line. More precisely, for each operator connection, sigma, there exists a unique operator monotone function, which is often called representing function of sigma, with this property. Furthermore, this one-to-one correspondence is an affine order isomorphism between the operator connections and the operator monotone functions. That is, if we have got two operator connections, sigma 1 and sigma 2, with f1 and f2 as representing functions, then a sigma 1b is less or equal than a sigma 2b if and only if a similar inequality holds for the representing functions. Moreover, if A is invertible, then we can write A sigma B, the connection A sigma B, in this form. This formula gives the characterization of all operator connections between positive operators. It's a very famous formula. And especially if sigma is operator mean, it happened if and only if f sigma 1 is equal to 1. And it implies that A sigma A is equal to A for all positive A. Moreover, sigma is a symmetric operator mean if and only if the above condition holds, and f sigma t is equal to f sigma t at the place 1 over t for all positive t. So with this, we have got the complete characterization of Kubo Ando, the bivariate Kubo Ando operator means and symmetric operator means by this formula. Let me see some fundamental examples. The simplest operator mean is the arithmetic mean. It is defined just like in the case of numbers. So this is the weighted arithmetic mean. Alpha denotes the weight between 0 and 1. And it's not hard to see that it's a Kubo Ando mean with representing function 1 minus alpha plus alpha t. And in particular, for alpha is equal to half, we have got a symmetric mean, which is called arithmetic mean. We remark that the generalization of the notion of arithmetic mean for more than 2 entries is quite obvious by this formula. It's not hard to see. Our second noteworthy example is the geometric mean, which is admittedly the most researched operator mean. Its weighted version defined by this formula. And the corresponding representing function is nothing else but the power function. And the symmetric case is the case of when alpha is equal to half. This is called the geometric mean. And it's not hard to see that if A and B commutes, then this formula goes back to AB on the half power, which forms like in the case of numbers. Several characterizations are known. For example, the following variational expression in terms of 2 by 2 block operator matrices. Here you can see that. And it was a long-standing open problem to extend the geometric mean to the case of more than 2 variables of matrices or operators. We will return to this question later. Finally, let's see our third example. The weighted harmonic mean is defined similarly to the scalar case. The corresponding representing function can be written in this form. And alpha is equal to half means the symmetric case. In this case, we can see the harmonic mean, which is very similar to the scalar case or the case of the numbers. Here, a variational characterization is also available. One can check that this formula characterizes the harmonic, the symmetric harmonic means. And the generalization for more than two positive operator is quite obvious in this form. It's easy to check that the following inequality chain holds for representing function of the harmonic, geometric, and arithmetic means, which implies, thanks to the Kubo Ando theorem, that the weighted harmonic mean is less or equal than the weighted geometric mean, which is less or equal than the weighted arithmetic mean. Furthermore, for an arbitrary operator mean sigma with representing function f sigma, f sigma is always between the representation function of harmonic and arithmetic mean. That is, the harmonic mean is the smallest and the arithmetic mean is the greatest mean among the Kubo Ando means. Now, let's turn to the notion of barycenters. The notion of barycenters, or least square mean, plays a central role in averaging procedure related to various topics in mathematics and in mathematical physics. In our case, motivation comes from statistics. We perform an uncertain measurement several times with outcomes in a metric space XD. And in this case, the most natural estimator of the quantity A we are interested in is the mean square estimator A hat. You can see here. And the goal is to solve this optimization problem. Here, the AJs denote the outcomes of the measurement. And slightly more generally, we can consider the following optimization problem, where the equivariant weight 1 over m are changed to arbitrary weight wj, where wj's are arbitrary weights, but in a lot of cases, the weights are probabilities, that is, they sum up to 1. It's easy to check that if we consider the n-dimensional real Euclidean space as metric space, then the barycenter is the weighted average, which is nothing else than the weighted arithmetic means of outcomes. In applications that involve measuring the dissimilarity between two objects, numbers, vectors, matrices, functions, distributions, etc., the divergence becomes essential. One such measure is a distance or metric, but there are many important measures which do not satisfy the properties of distance. A prominent example is the classical relative entropy, probability vectors, or Kullback-Leibler divergence. Here, the boldface P and Q stand for probability vectors with entries P1, P2, Pn, and Q1, Q2, Qn, respectively, between 0 and 1, and they sum up to 1. And in this case, we have got a similar result. That is, the barycenter of probability vectors Pj's is their weighted arithmetic mean. Now we can generalize this divergence in the following way. If we have got function strictly convex smooth function phi from the interval 0, 1 to R, we can define the so-called Bregman divergence. And we can compute, or we can solve the optimization problem with respect to this Bregman divergence, and we get the same result that the arithmetic means, the weighted arithmetic means of the probability vectors pj's is the solution of this this equation. And here it's an important to remark that the barycenter is independent of the function phi of the function phi here. And it's really a generalization, because here the classical relative entropy case that we mentioned above corresponds to the representing function x log x minus x. Now let's return to the matrix means. We have mentioned that the notable arithmetic, geometric, and harmonic means have got several characterizations. Now I like to show one of them, namely how can we characterize them as barycenters. It's easy to check that the arithmetic mean is the mean squared estimator or barycenter for the Euclidean metric. Moreover, just like in the scalar case, we can get them also as the divergence center with respect to the Bregman divergence. Here, the Bregman divergence is defined on positive operators as follows. We have got a differentiable strictly convex function on the positive half line, and with functional calculus, we can compute phi x and phi y and the Frechet derivative at the place y for x and y positive definite operators. And we take the trace, and this is the so-called Bregman divergences. Then for positive operators a, j, we get that the barycenter with respect to this Bregman divergence is the arithmetic mean. Now we turn to the geometric mean case, which is a little bit harder, because in this case we have to define a Riemannian metric on the positive definite matrices. Maybe the simplest way to construct an information geometry is to start with an information potential function and to introduce the Riemannian metric by the Hessian of the potential. There are many reasons originated from statistical mechanics, information theory, or mathematical statistics that the Boltzmann entropy is a candidate for being an information potential. A random variable x with probability density f is given, and its Boltzmann entropy is defined by this famous formula. It is also called by H functional. This is a particularly important functional. For instance, if we regard the heat equation, it can be seen as the gradient flow for Boltzmann entropy as potential. We will see that the positive definite real matrices might be considered as the variance of multivariate normal distributions or Gaussians. Indeed, if we consider centered multivariate Gaussians, centered means that with zero mean vectors, they have zero mean vectors. They are completely described by their positive definite covariance matrix A, and the density function of these Gaussians are given in this well-known form. And it's not too hard to compute the Boltzmann entropy of these random variables. And we can get the Boltzmann entropy in this form, where we use the notable expressions log that A is equal to trace log A. So finally, we can write it in the form half trace log A plus a constant depending on n, and was the dimension of our vector space. Sorry. Okay, for the sake of simplicity, we will identify these Gaussians with their covariance, and we will forget this prefactor half and this constant. And note that the n-by-n self-adjoint matrices equipped with the Hilbert-Schmidt inner product and the Hilbert-Schmidt norm is identified with the n-square dimensional Euclidean space. And the positive definite matrices, which will be denoted by Pn from now, form an open subset of this Euclidean space, and they form a manifold. And the Boltzmann entropy that was showed above gives a Riemann metric, define a Riemann metric by its Hessian. We can compute its Hessian in this form. And it's not hard to see that the tangent space of each foot point is the set of self-adjoint matrices. And finally, the metric induced by this Riemannian metric tensor is given by this formula and is often called Riemannian trace metric. So in this way, we have defined a Riemannian Riemannian metric on positive definite matrices. When we have got a smooth curve, its length, smooth curved gamma, its length can be computed this formula in the Riemannian geometry, which can be written in this form. And the global distance in the Riemannian trace matrix, or geodesic distance between 2 points A and B with respect to this Riemannian trace metric, is defined in this obvious way. And the curve gamma with minimal arc length is called geodesic. Here I can mention that this formula is independent of the choice of the parameter t of gamma. It's not hard to see. Now, several authors proved the following essential result. You can see here some of them: Korach, Portarek, Lawson, Lim, Batia, Holbrook, and Moaker. This result says that for each positive A and B, there exists a unique geodesic curve joining A and B, and it's given by this form, which is nothing else but the weighted geometric means of A and B. With this knowledge, we can compute also the geodesic distance between A and B. Indeed, the derivative is given by this formula, and the geodesic distance has a simple closed form in this way. Now we can observe that the midpoint of the geodesic curve joining A to B is exactly the geometric mean. But I like to remark that the Riemannian trace metric is not the only possibility the geometric mean as barycenter, or the geometric mean as barycenter. For example, the so-called S divergence defined by SRA is also a good choice. So the geometric mean is the divergence center with respect to S divergence, as was proved in this paper. Now, this barycenter interpretation allows us to define the geometric mean for more than 2 variables. So it was a long-standing open problem to extend the geometric mean to the case of more than 2 variables of matrices or operators. A breakthrough happened when Ando, Lee, and Matthias in 2004 proposed an iteration method to define a multivariable geometric mean. That paper was followed by the papers of Moaker, and of Batia and Holbrook, where the Riemannian geometry method was proposed to extend the geometric mean to multivariables. Here, I have to make some explanation. There are several different terminologies for multivariable geometric means in this Riemannian geometric approach. For example, Riemannian mean, least square mean, etc. Here are used the terminology Kercher mean because it seems like the most common name in the literature. So in this case, we have got M positive definite matrices, A1, A2, AM, so on, with weights W1, W2, Wm. And the Kercher mean is defined as the solution of this optimization problem. And by the knowledge of the Riemannian trace metric, we can write in this form. So the barycentric problem is to solve this optimization problem. That's why we have to find x0, where the derivative of this mean squared error function vanishes. This way. And keeping in mind this formula, we can get the Kercher mean as the solution of this nonlinear matrix equation called Kercher equation. The problem is that no explicit formula is known unless all the ages commute. But in this case, in this commutative case, the Kercher mean coincides with the geometric mean in this form. It seems for a good generalization for more than 2 operators. Similarly to the geometric case, we can define a Riemannian metric on positive operators by this formula, locally at A. This gives the infinitesimal arc length at A. And if we have got a smooth path on positive definite matrices, the arc length of this path can be computed with this formula. And we can define the corresponding geodesic distance as the infimum of this quantity, and here we vary the gammas joining A and B. One can check that in this case, the unique geodesic curve running from A to B is nothing else than the weighted harmonic mean. And we can also compute the geodesic distance in this turnout that is equal this B minus 1 minus A minus 1, and we have get the norm. Okay, so motivated by the examples above, our goal is to give a divergence center interpretation for every symmetric Kubo Ando means. For this purpose, we define a new divergence. Before doing that, we need to make some preparations. So if we have got a symmetric Kubo Ando means sigma with representing function f sigma, we know that we can write in this form, and it's a symmetric mean, and by the Kubo Ando theorem, we have got that it's equal to 1 and in 1, and the symmetry of sigma implies this equation. And hence, it means that the derivative at 1 is equal to half. Now we can define a function on G sigma on the range of f sigma with this integral formula. And the properties of f sigma above imply obviously that gay sigma shared these properties, that the gay sigma 1 at 1 is equal to 0, the derivative is the integrand, and the derivative in 1 is equal to 0. Now we are ready to define the following quantity with the help of the G sigma. That F sigma AB is equal to trace G sigma A minus half B A minus half when the spectrum of this quantity in the range F sigma, and is equal to infinity in the other cases. And this quantity F sigma is a genuine divergence in the sense of Emery. What does it mean? It means that satisfies the following conditions. At first, it's always greater or equal than 0, and it's equal to 0 if and only if A and B are equal. The first derivative of phi sigma is the second variable vanishes at the diagonal, and the second derivative of phi sigma, it's not the same, it have to be the same phi sigma, in the second variable is positive at the diagonal. These properties imply some convexity property of this phi sigma. We have proved that this new divergence phi sigma shares some further expected properties. I listed them here. The second one can be seen as some modular property of phi sigma. And here, the third one is interesting, that this new divergence is symmetric in its argument if and only if the sigma is the geometric mean. Now, we turn to the main result of this section, which asserts that the symmetric Kubo Ando mean A sigma B is exactly the divergence center of A and B with respect to this divergence defined before. So if we have got two positive matrices A and B, the barycenter of A and B with respect to this new divergence is nothing else but A sigma B, where sigma was a general symmetric Kubo Ando mean. That is, A sigma B is a unique minimizer of this function. This thing thanks to the convexity property. It was thanks to the convexity property. Similarly to the Kercher mean, this characterization of the symmetric Kubo Ando means naturally leads to a definition of weighted and multivariable versions of a large class of symmetric Kubo Ando means. So given a symmetric Kubo Ando mean sigma and a finite set of positive definite operators A1, AM are also given, and we have got a discrete probability distribution function, the distribution vector, and with these we can define the corresponding loss function denoted by Q sigma AW in this way. Okay, and now a technical remark. From now, we assume that the range of F sigma is maximal. That is, it's a positive half line. This technically implies that phi sigma is always finite, and so the quantity Q. And now we can define the weighted barycenter of operators with respect to the new divergence phi sigma as follows. It's clear that we take the argmin of the quantity Q sigma A W, as we have defined before. And this is called the weighted barycenter of operators A1, AM with weights W1 dots Wn. Now, how can we find the barycenter? We have to solve the critical point equation. Here, D stands for the Frechet derivative at the point X. It's absolutely similar to the Kercher equation that we get to the Kercher equation. That is, the equation to be solved can be right in this form. But we know that by the definition of G sigma, that it can be written equivalently in this disgusting form. I'm sorry. So it can be regarded as a generalized Kercher equation for this problem. And despite the complexity of the above equation, we can solve it some special case. So for example, when sigma is the geometric mean with the representing function square x, we can compute its inverse function easily. It's t squared. Remember that we need the inverse function of f sigma. And in this case, the critical point equation describing the barycenter corresponding to the geometric mean can be written in this easy form. And after rearrangement, after rearrangement, it can be written in this form. And we can observe that it's nothing else than the Riccati equation for weighted multivariable harmonic mean and arithmetic mean. And we know how can we solve the Riccati equation. So the barycenter coincide with the weighted so-called Kim-Lawson lim means, which is nothing else but the geometric mean of the arithmetic and the harmonic mean. Okay. At the end of my talk, let me list some further property of the barycenter. These properties are expected from a barycenter. The first one is the idempotency. So when all operator coincide, that the barycenter is A. It's homogeneous, so we can take T before the barycenter. The permutation invariance is also holds. And we have got a congruence invariance in this form. And it can be proved that the weighted multivariate harmonic mean is a lower bound for this barycenter. So that's all that I want to show you today. Thanks for your attention and thanks for your patience. And here you can see the supporters of our research. Thank you very much.
Yeah, thank you very much. And thank you for interesting talk. Now, I hope we have some questions from the audience. If you have questions, please feel free to ask our speaker. I don't hear any question.
Okay.
Yeah, that's fine. I have a question regarding in this paper. So you consider symmetric means, right?
Yes.
Yeah. So what happened with means which are not symmetric?
I don't know. So I don't know. This is my short answer. So we wanted to generalize the Kubo Ando means for in the not just the multivariable case, but for the weighted case too, and so that's why we start with the symmetric case.
Yeah.
Because when we have got a weighted, so we haven't got any. So maybe. So if it's not symmetric, all known exams for not symmetric means are the weighted means, I think.
It's like, you know, when I read your papers, your paper on this, just you construct some function g sigma.
Yes.
Then thanks to that function, you define the divergence. So where the symmetry is, where is the symmetry used in this presentation?
I think the symmetry is used when in the properties of G sigma. So for example, maybe you can see that when we define G sigma, so these all properties are used, and these comes from the properties of F sigma, which is implied by the symmetry of sigma.
Mm-hmm.
So that's why that we can use these properties of G sigma.
Okay, so the symmetry is this derivative of F sigma at 1 is 1/2. Is that correct? So that is the only thing you use. I think so. Symmetry.
Mm-hmm.
Because other than that, you know, like F sigma at 1 is 1. That is just, you know, property of the mean. And the only condition for symmetry is F's derivative at 1 is 1/2.
I think the symmetry is come from I don't know. Maybe you're right. Maybe you're right. Maybe you're right.
So yeah, I'm just curious because, you know, like symmetric means this is very small class. Small class, yeah. In the set of
yes, you're right. Now I don't see why we use just symmetric Kubo Ando means. I think it from this it seems to me that any Kubo Ando mean is working.
Yeah, I have the feeling like that. Yeah, I mean maybe you know we just need to rewrite this for any Kubo Ando mean, and then yeah maybe that works. So we don't have to restrict. I don't see any reason why we restrict, you know, consideration for.
So I think we restrict ourselves because we wanted to define weighted Kubo Ando means, which are not symmetric. So our starting point was the symmetric one, and with the help of this thing, we can construct weighted Kubo Ando means.
Mm-hmm. Yeah.
That's why we have written symmetric. But I think you're right that the symmetry is not so important. It not seems too important in this case.
Yeah. And another observation is that, you know, like we have a lot of non-Kubo Ando means. So actually we are trying. Well, my students are trying to construct quantum divergence, and we just want to have the same idea like your ideas in this paper. So like we pick any like well-known means like Hans mean or whatever, right? And then we try to construct that quantum divergence such that the fixed mean is the midpoint, is the solution of the least square problems. And I think that is difficult.
Yes. So here the Kubo Ando theory help us because this characterization is so good that we can construct this thing, but not for Kubo Ando means it should be difficult, I think. Yes.
Yeah, I think so. Not every Kubo Ando mean,
Yeah.
All right. Do you have any questions for our speaker? I don't see, Osaka here. I think he's.
Yeah, I have some comment. So.
Oh, you are still here? I see.
Yeah. I'm still try to not sleepy. I'm sleepy, but I try to have a give a comment. So you don't know. You say that so you don't know how to construct non-symmetric Kubo mean, but so we can easily I know how to construct non-symmetric mean. That means that given a two symmetric mean, then so we can construct the non-symmetric mean between symmetric mean. So we already published one paper proceeding AMS. So if you are interested in, then you may check it. So that's why. So I think as Hua said. So I think you can extend your result to a non-symmetric mean. Yeah, your result is very beautiful. So using this function of G sigma, then in some sense you characterize a symmetric mean using the very center. That is very beautiful. And but I hope so. Once I try to prove that, so I try to extend your result for non-symmetric mean, but I couldn't. But I think there is another way to define another G sigma. Then we can get another characterization of non-symmetric mean. I hope so. So that is my comments.
Thank you.
Yeah. So that means that rational number is dense in the real number. That situation is the same. So non-symmetric is in some sense dense in operator means. So easily construct non-symmetric mean between symmetric. So yeah, if you are interested in, please check my paper.
Your recent paper?
No, not recent paper. So that is 5 years ago or something. So I wrote a paper with WADA.
Oh yes, on kind of transformation. Is it correct? You use. I don't remember the name of the transformation. Yeah, probably I saw.
That is we use a method of Barber transformation.
Yeah, probably yeah.
Yes. So then easily construct non-symmetric means.
Interesting.
Yeah. But I think your result is very interesting. I try to extend your result. So thank you for your talk.
Yeah, thank you. Very good. So do you have any questions for our speaker? I don't think that we have more. So I would like to thank you again.
No, I'm sorry. I have a question.
Okay.
Sorry, I don't follow clearly at the beginning of the presentation, but I understand that there's always unit solutions of the problem of the least square problem, the least square sum of and positive matrices for symmetric and Kubo Ando being, and the presenter introduced the divergence, and I'm considering if there's the solutions of the least square sum of and positive matrices for some divergence, and more than if their solutions, if we can finding the boundary center for and positive matrices with some divergence. Do you consider about this the problem?
Yes, I think. So, the connection was not so good, so I don't hear everything. I can't hear everything, but what was the question? Sorry.
Repeat the question or what?
I'm sorry, I can.
I can't hear you.
Yeah, would you please repeat your question? Boy?
Yeah. Yes, I'm considering about the problem of finding the boundary center of n positive matrices with some divergence, not the symmetric Kubo Ando mean. Or can we find the solutions of the problem of the least square sum for divergence, not symmetric mean Kubo Ando?
So as understood, so you want to consider another diversion and you want to solve the least square problems with respect to that diversion. Is that correct?
Yes, any divergence.
Okay.
So it's a hard problem. So in general, when we have got any divergence, to find the barycenter, it's a hard problem. So there was I have shown 3 examples, and here. So for example, when we have got when we choose the Euclidean metric, then we have got the barycenter as the arithmetic mean. When we like to find the barycenter with respect to Bregman divergences, we also have the barycenter as the arithmetic mean. In the Riemannian trace metric, the barycenters are the geometric means. And finally, when we look for the barycenter with respect these other Riemannian metric, the barycenter will be the arithmetic mean. So in this case, the solution of the barycenter problem are known, but we change our mind and we try to construct a divergence for what the given symmetric Kubo Ando means will be the barycenters. So that happened here. For any divergence, if you try to solve the barycenter problem, an arbitrary divergence, it should be very hard. It depends on the problem.
I think such problem, the least square problems, is well known in differential equations, differential geometry. But the difficulty is how to realize those pictures. I think so. It's like you presenting here for some specific means. Yes, you solve the least square problems to the end, right? But in general,
yes, there is a lot of so for some divergences, for example, the Hellinger distance, yeah, or Burroughs metric or something else, we can compute the barycenter. So we can get the so-called Wasserstein mean and etc. In the case of Wasserstein 2 metric. So in a lot of cases we know the solution, but generally I don't know what can we say about this.
Okay, I still have one more question, and then
Yeah.
so let's go back to the scalar case.
Yes.
The situation is, if we just consider scalar case, or you have suppose that you have 2 points, right, on the some kind of A and B, and similar to the idea in your paper, we pick any point in between, right, A and B. So I think we can construct means, right? We can find a mean, or we can construct a divergence such that that point is the midpoint of A and B with respect to that divergence.
Mm-hmm.
Do you know that result or not? Even for scalar case.
I don't know. It should be. It should be in the scalar case. I don't know. It's a well-known thing, or.
Like, for example, if you consider symmetric means, right? So that is kind of, that is the line in between the harmonic mean and then the arithmetic mean. But if we consider scalar case, the midpoint is arithmetic mean. The arithmetic between arithmetic mean and the point, which is bigger than arithmetic mean, we still have a lot of points there. So so my question is, if you know some kind of that, even for scalar case, so how to construct a divergence on the number line so that each point in between A and B will be the midpoint of A and B.
Mm-hmm. I understand your problem, but I don't know the answer. It's a very good question. I don't know any result about this problem, but it's a good question. I will think about it, and if I find something, I will write for you. Okay.
Yeah, I think if we understand that picture, even for scalars, we might have some idea how to generalize to a non-symmetric Kubo Ando. I guess so. All right.
Yes.
Yeah.
Okay.
All right. Thank you very much for your interesting talk.
Thank you.
Yeah, and I hope and thank you everyone for being here today. I hope you enjoy the talk, and we see you next week.
Okay.
Thank you very much. Yes.